Case Western Reserve University's Institute for the Science of Origins proudly presents the Origins Science Scholars Program. The Institute advances the scientific understanding and application of the origins and evolution of human and natural systems. The Origins Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and MediaVision. My pleasure to introduce Dr. Nicole Yunger-Halpern, a National Institute of Standards and Technology physicist working at the Joint Center for Quantum Information and Computer Science at the University of Maryland and adjunct assistant professor of physics at the University of Maryland. Dr. Yunger-Halpern re-envisions 19th century thermodynamics for the 21st century using the mathematical toolkit of quantum information theory. She applies quantum information thermodynamics as a lens through which to view the rest of science, gaining new perspectives on atomic, molecular, and optical physics, condensed matter, chemistry, high-energy physics, and biophysics. She calls this research quantum steampunk, after the steampunk genre of art and literature that juxtaposes Victorian settings with futuristic technologies. Her talk tonight is entitled Quantum Steampunk, the Physics of Yesterday's Tomorrow. Please join me in welcoming Dr. Yunger-Halpern.
Thank you for the kind introduction. Thanks very much for the invitation to speak here, and thanks especially to all of you who have chosen to attend either in person or on Zoom. I spent a year studying physics here in a city called Waterloo in Canada near Toronto. Waterloo excels in theoretical physics, tech startups, and I say this as a person who grew up in Florida, winter. Lots and lots of winter. But eventually the winter ends. One day in the spring for a study break, I visited the Waterloo Public Library. There I found this novel by the Canadian poet J. Ruszewski, The Wolfenburg Clock. One scene takes place in Austria during the 1800s. The inventor is standing on a balcony, gazing down at the ballroom below that he's converted into a workshop. This inventor and his family members build automata, clockwork-driven elephants and snakes and so on. So this inventor is gazing down on his miraculous creations with his overcoat trailing out behind him, and the atmosphere is just palpable. And for good reason. Shortly after I read that book, I realized I encountered steampunk. Steampunk is a genre of literature, art, and film. Steampunk stories take place during the Victorian era, when the Industrial Revolution has been humming. Some of the earliest factories are belching smoke. London is full of smog and Sherlock Holmesian mysteries. Railroads are cutting across the American West for the first time, and people wear waistcoats or petticoats. Against this backdrop are futuristic technologies, automata, time machines, flying ships, and submarines. Another Canadian poet, Douglas Featherling, has supposedly said, "Steampunk is a genre that imagines how different the past might have been had the future come earlier." You might have encountered this steampunk novel, The Time Machine by H.G. Wells. It was one of the first steampunk works as it was written during the 1800s. But steampunk is very much with us still. The Invention of Hugo Cabret was a New York Times bestseller during the early 2000s. Enola Holmes was one of the first films released on Netflix due to the pandemic. It features Sherlock Holmes's little sister, Enola. So the film was a hit. The sequel is actually coming out on Friday, so I am going to be watching it this weekend. And The Nevers is a show on HBO about Victorian women who have supernatural gifts. These works reach back to the past and ahead to the future. This fusion of old and new creates a wonderful sense of adventure and nostalgia, exploration, and romance. So fans dress up in steampunk costumes with top hats and goggles and gears and gather at steampunk conventions for the sake of a fantasy. But this fantasy is becoming a reality in my field of research. I'm a theoretical physicist. I model the universe with mathematics and then look for features of the world that weren't known before that surprise us. These features often crop up in extreme settings, such as at very low temperatures and in systems of just a few atoms or ions. Specifically, I work at the intersection of three fields: quantum physics, information science, and energy science, or thermodynamics. I'll briefly preview this intersection and then explain it in more detail. Information science is the study of how efficiently we can process information. For instance, solve computational problems and protect information. Quantum physics is the study of the very small, such as single atoms and ions. They behave in counterintuitive ways that are impossible for everyday objects. Scientists and engineers are leveraging these counterintuitive behaviors in quantum information science. In quantum information science, for instance, we're building quantum computers, which will process information in ways that familiar technologies, such as my laptop, cannot. Thermodynamics is the study of energy. It was developed during the Victorian era to describe one of the transformative technologies of the era, namely the steam engine. Today's transformative technologies include quantum devices, which are very, very different. So we need to re-envision the thermodynamics of the 1800s for the 21st century. We need to ask how quantum engines could look and what they could achieve. In other words, we need to reach back to the past and ahead to the future. The resulting fusion of old and new, I call quantum steampunk. So a genre of science fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. Let's look at each of those components more closely. Information science is the study of how efficiently we can perform information processing tasks. These include solving computational problems, such as calculating a satellite's trajectory, communicating information, such as via Zoom, securing information cryptographically, and storing information in memories. We live in the information age, but what is information? It's basically the ability to distinguish between alternatives. Say that a friend asks whether the pub down the street, in Victorian London, of course, is open or closed. You peer through the window and see either foaming mugs or cleaned mugs sitting upside down on the counter. You've gained the ability to distinguish whether the pub is open or closed. So you've gained information. We measure quantities in units, such as seconds or teaspoons. What's the basic unit of information? It's called the bit. It's the amount of information you gain if you have no idea of the answer to a yes or no question, and you learn the answer. Say that when your friend asks about the pub has a probability 1/2 of being open and a probability 1/2 of being closed. When you peer through the window, you gain a bit of information. We encode a bit in a physical system that can be in one of two possible states, such as a thumb that's pointing upward or downward. In a familiar computer, we encode a bit in a transistor that has the value 1 or the value 0. Quantum computers store information very differently. Quantum physics is essentially the study of really small things, such as single atoms or electrons or particles of light called photons. These systems behave in ways impossible for everyday objects, such as books and microphones and human beings. Everyday objects are large, are massive, and consist of many, many particles. We call them classical. Quantum systems are non-classical. What are these counterintuitive quantum behaviors? We can begin to grasp one by imagining that some young physicist, let's call her Audrey, has an electron, and her brother Baxter has another electron. The siblings can perform some operation on their particles that creates entanglement between them. Entanglement is a relationship that quantum particles can share and classical particles cannot. Entanglement creates strong correlations between outcomes of measurements. Here's a glimpse of how it works. Suppose that Audrey measures some property of her particle, and the measurement has two possible outcomes, which we'll label as 1 and 0. For instance, Audrey can measure whether her particle has a lot of energy or just a little energy. If the two particles are entangled as strongly as possible, then Audrey will have no idea which outcome she'll obtain. 1 and 0 have 50-50 chances. Now, suppose that instead, Audrey measures her particle and Baxter measures his. Now, the two siblings can predict something about the joint outcome. In one example, if Audrey obtains a 1, she'll know that Baxter will obtain a 0. And if Audrey obtains a 0, she'll know that Baxter will obtain a 1. Furthermore, there is a measurement that the siblings can perform jointly on the pair of particles together, such that the siblings can predict the outcome with certainty in advance. So there's something, some information that isn't in Audrey's particle, it isn't in Baxter's particle, it isn't even the sum of the two particles addressed independently. It's spread across the pair. When it comes to entanglement, the whole really is greater than the sum of its parts. Scientists and engineers are now leveraging entanglement in quantum information science. Quantum information science is the study of how we can use quantum phenomena to process information in ways forbidden for classical systems. Quantum information technologies include quantum computers, networks for communication, cryptographic systems, and more. Quantum computers will be able to solve in minutes certain problems that cost even supercomputers many, many years. Today's quantum computers are small and limited. Many of us in the field think that we'll need quite a few more years to build them up to their full potential. Applications will include information security. If you've purchased merchandise online, say through Amazon, your credit card information has been secured with a common cryptographic protocol. Classical computers can't break that safeguard in any reasonable amount of time, to the best of our computer science knowledge. But a quantum computer will be able to break that safeguard easily. On the other hand, quantum phenomena provide new resources for protecting information. In 2017, researchers in China and Austria conducted the first video teleconference encrypted with quantum resources. An important application of quantum computers will be to research and development in material science and chemistry. As a thermodynamicist, I feel obliged to point out that one of the most ambitious potential applications is to energy use. Microsoft's quantum team detailed this idea. In some countries, food security is at crisis levels, especially today. In other countries, food security is at some of the highest levels ever in history. So fertilizer is extremely important across the globe. We invest about 3% of the world's entire energy output in fertilizer production. Why do we spend so much energy? Because we produce fertilizer using an old technique from 1909. Bacteria can accomplish the same goal much more efficiently. But those bacteria use a molecule that's too complicated for us to simulate on classical computers. The molecule, though, is quantum. So a quantum computer will naturally be better suited to unlocking the molecule's secrets. And if all goes as hoped, and that is a very, very big if, then transforming fertilizer production and energy use. Suppose that we use quantum sensors to gather information about a system, maybe a biological system, then we could process that quantum information using a quantum computer. And could this have application to something like the study of genes? There have recently been studies of these fully quantum experiments, even in the paradigm of performing many, many trials. Suppose that you perform a trial, collect quantum information about it, store that in a quantum computer, perform your next trial, and so on, and enable entanglement across trials. Some people at Caltech and Harvard and elsewhere have been studying that paradigm, and they show that there are some computational advantages that you can gain. According to my understanding, some of the most promising possible applications of quantum computers are to quantum chemistry, and those are also some of the problems that people think that quantum computers will be able to help with first, as we increasingly build quantum computers up to their full scale, when they can tackle a much larger range of problems. I'm not familiar with applications to the study of genes in particular, but certainly to to chemistry in general, there are a lot of proposed applications. When we produce fertilizer, we need nitrogen in a specific form called its fixed form. But nowadays, people take nitrogen, say, from the air and spend a whole lot of energy on fixing it. Bacteria have been fixing nitrogen for much, much longer than we have. Again, we've been doing this the protocol that's used today was invented only in one sense, only in 1909, but in another sense, it was developed in 1909. One would think that we might have advanced since then. The bacteria use this molecule called nitrogenase, but again, it's a pretty complicated molecule. If we could figure out how it works, then we might be able to take advantage of what it's doing in our artificial fixing process. So that's the goal. My quickest, honest example is the one that I gave in the slides. But very loosely speaking, in a cartoon sense, entanglement is something such that if I have a particle that's entangled with a particle of yours, we bring our particles arbitrarily far apart, say the opposite sides of the country, then if you measure your particle, loosely speaking, in a cartoon sense, my particle changes instantaneously. You cannot transmit information to me instantaneously, and that can be the basis for another question in the next question and answer session, but some influence, my particle is affected, so to speak, instantaneously. But I really think of entanglement as information that's not in one particle and not in another particle, not in the sum of the particles addressed independently, but in the whole, or between the particles, in the relationship between the particles. Before the question and answer session, we saw that quantum computers will have applications to cybersecurity, research and development, and potentially energy use. Little wonder that governments across the globe are pouring funds into quantum science, technology, and education. In 2018, Congress passed the National Quantum Initiative Act, which provided $1.2 billion for quantum efforts. Even more astoundingly, the Senate passed the act unanimously. So everyone in the Senate actually agreed on it. Not only governments, but also loads of companies are investing in quantum science and technology. Microsoft, Google, IBM, Amazon, and Honeywell have quantum teams. Quantum startups are booming. At least 2 have become publicly traded in the past few years. One example is Rigetti, whose team is shown here back in March when the company debuted on the stock market. This object belongs to IBM. This is not a quantum computer, even though it looks cool enough to be one, doesn't it? Actually, a number of people think this looks steampunk because of the gold and copper and wires sticking out. This object holds a quantum computer, which fits on a small chip. That chip needs to be at low temperatures in order to support quantum phenomena such as entanglement. So this device cools the quantum computer to temperatures lower than that of outer space. This device is called a dilution refrigerator, or to those of us in the fields, a fridge. Actually, when my husband heard that, he's a classical computer scientist, he was indignant. He said, this cools things down to temperatures below that of outer space, and you can't even call it a freezer. Anyway, cooling leads us to the third element of our triumvirate, thermodynamics. Thermodynamics is the study of energy, the forms that energy can be in, and the transformations amongst those forms. Objects can transmit energy in 2 forms, heat and work. Heat is the uncoordinated energy of particles jiggling about randomly. Heat is disorganized energy and so isn't directly useful. Work is coordinated energy that can be directly harnessed to power a factory or charge a battery or raise an anchor. Heat engines convert random heats into coordinated work. Heat engines drove the Industrial Revolution by powering the first factories. Around that era, people started wanting to know how efficiently engines could operate. So they developed the theory of thermodynamics, giving it a practical bent. But the practical questions then led to fundamental questions, such as, why does time flow in only one direction? And do materials really consist of particles too small for us to see? The theory of atomism hadn't been entirely accepted by the Victorian era. Cooling, spelling heat, is a thermodynamic task. But how do you measure the energy emitted by a quantum system that's cooling? You can measure the heat emitted by a classical system by measuring the system's energy, cooling the system, and measuring the energy again. The initial energy minus the final energy is the heat lost. But quantum systems are more delicate than classical systems. You might have heard of Heisenberg's uncertainty principle. Werner Heisenberg was a German physicist who helped found quantum theory during the 1920s. He intuited that if you measure a quantum system, you disturb it. If you measure a quantum system's energy, you might change the energy. And so if you try to measure the amount of heat absorbed by a quantum system, you probably change the amount absorbed. So how we can measure quantum heat, or even conceive of quantum heat, is not straightforward. Furthermore, this fridge is a large classical system. What if we tried to build a fridge from a quantum system? Could we? How small could we make it? Could quantum phenomena such as entanglement benefit a quantum fridge, as they benefit quantum computers. More generally, just as there are information processing tasks, such as encrypting information, there are thermodynamic tasks, such as refrigerating and charging batteries. Given that quantum phenomena benefit information processing tasks, can they benefit thermodynamic tasks? And how can we extend the Victorian theory of thermodynamics from large classical systems, such as steam engines, to small quantum and information processing systems? These questions underpin quantum thermodynamics, my field of research. This field, I think, shares its aesthetic, or really its spirit, with steampunk, hence the name quantum steampunk. How and when did quantum thermodynamics develop? The field has roots that stretch back to the 1930s. Right after quantum theory was formulated, people began wondering whether it could explain thermodynamic phenomena. During the 1950s and 60s, researchers designed the first quantum engine. It consists of one atom that you can use in a maser. A maser is like a laser, shown here in its all-important task of driving a cat insane. But whereas a laser emits visible light, a maser emits microwave radiation. The atom absorbs heat from a hot environment and emits some of that heat to a cold environment. The rest of the heat is converted into well-organized energy, work. It turns out an engine doesn't need gears and cogs and other moving pieces. It needs only one atom. Over the ensuing decades, quantum thermodynamics had a small following. It wasn't seen as a discipline. Some people even said that quantum thermodynamics is an oxymoron. Thermodynamics was developed to describe large classical systems, such as steam engines, so thermodynamics couldn't possibly have anything to say about quantum systems. However, over the past decade, quantum thermodynamics has experienced a boom. Here's a photo from my community's big annual conference in 2018. We met in Santa Barbara that year. That's why the scenery is gorgeous. We form an international community with hotspots in the United Kingdom, Germany, Israel, Brazil, Switzerland, and elsewhere. A few of us quantum thermodynamicists work in the United States. The US broadly is starting to catch on. Colleagues in particle physics, materials physics, and more are starting to incorporate quantum thermodynamics as a new twist into grant proposals, conferences, and research programs. In fact, at the University of Maryland, we established North America's first quantum thermodynamics hub this September. We aim to become the local watering hole for those learning about quantum thermodynamics, airing their best new results, and creating a community across North America. Why has quantum thermodynamics been booming? Quantum information science matured in the early 2000s. It came to offer a mathematical and conceptual toolkit for understanding quantum systems through how they store and manipulate information. Quantum information science also came to offer unprecedented experimental opportunities. Labs achieved exquisite control over tens to hundreds of thousands of atoms or ions. We've been using all these tools of quantum information science to build and test a theory of quantum thermodynamics. Here's an example of something we can achieve in quantum thermodynamics. We'll start with a classical story that showcases the interplay between information and energy. Then we'll see what quantum physics adds. We can store a bit of information not only in a transistor, but also in a gas particle in a box. Suppose that this particle is classical, like a miniature basketball. This is a really, really simple gas. If the gas is on the box's right-hand side, we'll say that it encodes a 1. If the gas is on the left-hand side, we'll say that it encodes a 0. By the way, this illustration, like the other black and white illustrations that we've seen, is by Todd Cahill. Todd is a steampunk artist. He illustrated my book. He had no experience with quantum physics whatsoever, so the process was an adventure, but I think he succeeded in making really gorgeous illustrations. Suppose that we have no idea where the particle is. It can be anywhere in the box. Its position is totally random. And suppose that we want to reset the particle's position to the box's right-hand side, a nice, clean state. This is like taking a sheet of scrap paper that's been scribbled on totally randomly and erasing it to a nice, clean state. To erase the bits encoded by the gas, we let the gas exchange heat with its surroundings, which have a fixed temperature, through the box's walls. Then we slide a partition into the box near the left-hand wall and push the partition to the box's center. The gas ends up trapped in the right-hand side. At what cost? We're compressing a gas, so we have to exert energy, namely work, the coordinated, useful type of energy that can be transferred between systems. So we spend work to reset the particle's position, to erase the bit of information. In other words, erasure, an information processing task, costs work, a thermodynamic resource. What's more, suppose that we want to compute and compute and compute and compute. Eventually, we'll run out of scrap paper. The universe doesn't contain an infinite supply of scrap paper, so we'll have to erase some. We just saw that erasure costs thermodynamic work. So computation has an intrinsic thermodynamic cost. When I first learned that, in my first quantum computing course, senior spring of college, I was staggered because a priori, information and energy seem like they don't necessarily have anything to do with each other. But they turn out to be inextricably bound up. Rolf Landauer, an information scientist at IBM, realized this in 1961. The process that we just saw is called Landauer erasure. Landauer was actually a skeptic of quantum computing. He believed that quantum computers would be so finicky that no one could ever control or build one. My community intends to prove him wrong about whether quantum computers can work, but he does seem to have been right about the role of work in computing. Until now, I've told you a story about a classical gas in a box. But gosh darn it, this talk is called Quantum Steampunk, so quantum physics has to be able to do something for us. So what can quantum physics add? We'll address that question after the next question and answer session. There is an impression that can get out that entanglement can enable communication to happen more quickly than light can travel. That's incorrect. It's very easy to get that impression, but as far as we know, information cannot propagate more quickly than light can. Light still, to the best of our knowledge, provides the ultimate speed limits in the universe. Here's an example that can help us see or hopefully buy the idea that entanglement cannot enable us to communicate more quickly than light. Suppose that you have a particle and I have a particle. We entangle the particles, we bring the particles very far apart, and then you measure your particle. We said that in a cartoon sense, loosely speaking, we can think of my particle as changing instantaneously. So couldn't you send me a message instantaneously? The answer is no, because there are ever so many ways that I could measure my particle, and I must measure my particle in order to get any information out about it. So if you measure your particle in a certain way, then by measuring your particle, by performing some operation on your particle, together with the entanglement, you're trying to send me a message. But I need to know how I'm supposed to measure my particle in order to get the message out. If I make the wrong message, or excuse me, if I make the wrong measurements, then my outcome could be totally random. And so I'll have absolutely no idea what message you are trying to send. So you need to send me information about what measurement I should perform. And you can do that no more quickly than light can travel from you to me. Quantum batteries are, they've experienced a surge of interest theoretically over the past few years. I know there's been at least one experiment that has involved either a quantum battery or a close analog of it. So experimentalists are working on it, and personally, I expect to see a number of papers in the next few years. Also, chemists talk a lot about quantum batteries, but unfortunately, the quantum thermodynamic community interested in quantum batteries and the chemistry community interested in quantum batteries are pretty disconnected. I am also hoping that we will grow connections within the next few years, so they also might be able to tell you a whole story about their quantum batteries and experiments they're on. There's been a result in quantum thermodynamics that shows if you have a bunch of quantum batteries and you want to charge them all, then you can charge them at a greater power if you entangle them than if you don't entangle them. Before the Q&A session, we saw that information can be used to turn random heats into coordinated work. But what if we add quantum physics to this mix of information and energy? The story can change in multiple ways, depending on which kind of quantum resource we have available. I'll share one change discovered by colleagues of mine, including the Portuguese physicist Lydia Del Rio. Suppose that we want to erase not a classical bit of information, but a quantum bit, a qubit, a basic unit of quantum information. A classical bit encodes the answer to one yes or no question, such as, is the pub down the street open? A quantum bit encodes the answer to each of infinitely many yes or no questions. However, you can only ever access one question's answer. As soon as we learn that answer, as soon as we interrogate the qubit, we disturb it, according to Werner Heisenberg. So the system will no longer carry all of the information that it used to. Still, the qubit encapsulated more information in some sense than a classical bit could. We just need to be clever about how we manipulate and interact with the qubit. So we can encode a qubit in an electron, such as Audrey's particle from a few minutes ago. Audrey's qubit can be entangled with Baxter's qubit in some fixed temperature environment. Remember, if Audrey's qubit is entangled as strongly as possible, and then she measures her qubits, she has no idea whether she'll obtain a 1 or a 0. The outcome is totally random. So Audrey's qubit resembles the gas particle bit, whose location, right or left, 1 or 0, was totally random. Just as we could erase the gas particle bit, Audrey can erase her qubit. My colleagues proved that Audrey can erase her qubit while gaining work that she can use to charge a battery or lift a tiny weight. This result should surprise us. Landauer said that we have to spend work to erase information. The trick is to sort of burn the correlations between the particles. Entanglement serves as a kind of thermodynamic fuel together with heat. You've probably heard that entanglement was the focus of this year's Nobel Prize in Physics. 3 experimentalists shared the prize. They demonstrated that classical physics cannot accomplish something that entanglement can. And their work paved the path for quantum computing, which in turn provided a model for this quantum thermodynamics. The quantum phenomena, including entanglement, can serve as resources in thermodynamics, in gaining work, as well as in information processing. Beyond erasing information, we can build quantum thermodynamic engines, refrigerators, ratchets, and batteries. The quantum phenomena can benefit such devices, my community has found. We can use entanglement as a resource in refrigeration, a quantum engine that, so to speak, burns information can perform more work on average than its classical counterpart. And quantum engines can operate under conditions in which classical engines cannot. These results not only help us extend Victorian thermodynamics into the 21st century, but also shed new light on the discrepancy between the quantum world and the classical. If we gaze into the future of quantum steampunk, what do we see? First, this field has been gaining energy and momentum sight unseen over the past decade. I expect the field to continue this upswing and increasingly join the ranks of established fields of physics, such as astrophysics and elementary particle physics, and as of a few years ago, even quantum information science. Some of us quantum thermodynamicists are building bridges to long-established disciplines. Just as quantum information science has offered a new lens through which we've seen other fields, such as thermodynamics, we're now using quantum thermodynamics to understand black holes and chemistry and more anew. For instance, I had the pleasure and privilege of collaborating with a chemist at the University of California, Berkeley, David Limmer. So David studies molecular switches. These are small molecules that appear across nature and are also applied in technologies. For instance, we have them in our eyes. Much of the time, a molecular switch would be in this configuration. The sphere represents atoms, and the rods represent chemical bonds. Upon absorbing a photon, the molecule has the opportunity to switch configurations. That switch can set off a cascade of biological processes that can end with the experience of vision. David wanted a simple general bound on the probability that a molecular switch would switch. We derived that bound using mathematical tools from quantum thermodynamics. So a first grand opportunity is to expand quantum thermodynamics far beyond its original boundaries. Second, quantum thermodynamics has its roots in theory. From quantum thermodynamics, we've gained fundamental insights into what distinguishes quantum from classical physics what it means for time to flow, and more. But quantum thermodynamics is growing increasingly experimental. Experiments are testing the theory and sparking new theory. Personally, as a theorist, I've collaborated with 4 quantum labs over the past 3 years. One lab uses photons, one uses ions, and 2 use artificial atoms. We have many options, and I expect the community to take advantage of them increasingly. Most of the experiments happening now are proof of principle. They show that we can realize quantum engines if we try very hard, but those engines aren't practical. They perform less work, then we have to invest in cooling the engines down so they exhibit quantum behaviors and then manipulating them. So a third opportunity is to make quantum thermodynamics practical. The original theory of thermodynamics went hand in hand with the Industrial Revolution, which was eminently practical. Quantum thermodynamics should go hand in hand with similar utility. For my part, I'm working with experimentalists in Sweden on a quantum refrigerator for cooling quantum computers. I mean, you would expect folks in Sweden to excel at cold and refrigeration. Suppose that the quantum computer inside this classical refrigerator has just finished a computation. Its qubits are used up. To reset the qubits, we have to cool them even more. We can put a quantum refrigerator inside the classical refrigerator to reset the qubits. The quantum refrigerator, being inside the classical refrigerator, is already cold enough to exhibit quantum behaviors. So we don't need to spend extra work on cooling it down. Furthermore, the quantum refrigerator is autonomous. So it operates on its own without a need for external control or work. So the quantum refrigerator can benefit our quantum computer at a relatively low cost. The experimental test of our theory actually happened this month and last month at Chalmers University in Sweden. It's these sorts of opportunities to apply quantum thermal machines that colleagues and I are now pivoting toward looking for. Quantum thermodynamics is an incredibly exciting emerging field. It is vibrant and growing. It offers both fundamental insights and technological opportunities. If you'd like to learn more from my book, then the folks at home can obtain a discount by using this code if you order directly from Johns Hopkins University Press. Those who are attending the talk in person can purchase copies right here, and I'd be happy to sign them after the talk. When I was a master's student in Waterloo, I read about steampunk in a novel. But this genre of fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. The fantasy of steampunk is becoming a reality. Thank you. How exactly one entangles 2 particles depends on what sorts of particles one has. One could have ions that are trapped by lasers. One could have ultra cold atoms. One can have artificial atoms of multiple types. So the entanglement mechanism depends on the experimental platform. But in general, entanglement is created by a force. We're all familiar by forces. For instance, we know that if we have 2 charges, 2 positive charges, say, then they will repel each other. If we have a positive charge and a negative charge, then they'll attract each other. It's these sorts of forces that can create entanglement. It all depends on which system you're using. Oh, right. The question is about to what extent entanglement requires energy? The answer to that, again, depends on exactly what sort of system you have in front of you. If you are a theorist, then you can say that the particles are energetics are like so, and you could even imagine a system in which entanglement doesn't require any energy. If you are talking about particles, let's say atoms, such that the qubits, the information, is stored in a system's energy levels, then creating entanglements might cost energy. But again, it depends on exactly what physical system is in front of you. I should re-emphasize the hedging that I have made throughout these question and answer sessions. We say that kind of in a cartoon sense, the second particle changes instantaneously. If you want to get into the nitty-gritty details with experts, there are some who will argue with you, but that's kind of a loose way of seeing the situation, and it's kind of accurate enough. How do we know that this change is instantaneous? I personally am not aware of whether experimentalists have tried timing or have tried creating experiments in which they make one measurement over here and then measure over here after some particular period of time. I could say the Nobel Prize in Physics for this year was awarded for Bell tests. These are experiments that require the two entangled particles to be measured very far apart from each other, so that in between the measurement over here and the measurement over here, there is not enough time for light to propagate. So we know that no influence can have gotten from here to here via the usual means. And yet, these experiments show that the particles were able to accomplish something. They had stronger correlations than could be achieved with any classical systems. That was you can prove theoretically that if you have entanglement, this is possible. And experimentalists actually did manage to separate the measurements by enough time, or by a time such that no light could have traveled from one measurement to the other. And yet they found that the particles were able to accomplish something that no classical particles should.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.